Hello again, this is session 20, page 322, and this is the page where we'll put everything together here for logs. Really nice page, a lot of nice examples too. And notice that I've kind of started a little bit differently. First of all, you see, as usual, a log's an exponent, right? Remember that one. And I didn't put all the rules on the board. I needed more space at this point. However, you should know those rules. What the definition is, changing from a log form to exponent form. If you're multiplying with the numbers, you'll be adding the logs, dividing, you subtract the logs, and taking to a power, you multiply the logs. And then our change of base we talked about last session also. Kind of go back and review now for session 20, page 322, at least a few of the first few problems. Notice that I started with number 7 instead of number 3. I think the author kind of put these out of order a bit because 7 is a lot easier than 3. Although you should be able to do both of those anyhow. For number 7, we have the fact that 7 to the 2x minus 5 equals to 7 to the 3x minus 4. And the reason I chose this, of course, is because you see that they have the same base. And our rules say, look, if they have the same base, then the exponents must be the same. So we're going to match the exponents here and say that 2x minus 5 should equal to the 3x minus 4. And then we'll try to get the x's together and the numbers away. Probably maybe subtract 2x from both sides, I guess it'd be nice. Subtract 2x from both sides, you get x here on the right. And then maybe adding 4 to both sides. How about x is negative 1, okay? So it looks like that should be a nice answer for us. X is negative 1. You could put it back here to check to see. Put a negative 1 here, that's negative 2, negative 5, negative 7. 7 to the negative 7. Put a negative 1 here, negative 3, negative 4, also 7 to negative 7. Looks good. A nice answer for number 7, very basic. If you have an equation where, in fact, it looks like we have a lot of 7s there, the problem 7, and the author also put 7 in for the base. The bases are the same, the exponents must also be the same, match those, and you're finished. Number 3, not quite the same. This, I believe, on the problem, I'll check in just a moment. The problem, I think, was the 27 over 8 for number 3. 3 is, yes, 27 over 8. What I did there was I changed 27 over 8 to 3 cubed over 2 cubed, 27 over 8. And the reason I did that was because I saw the 3 and the 2 and the base on the other side. And just as in number 7, we like to try to get those bases to be the same. Since they're really not the same, we'll do what we did in the last session to consider the negative situation. And so that instead of the 3 cubed over 2 cubed, this could of course be 3 over 2, the entire quantity cubed, if you want to do it that way. It's still the same thing. Maybe move the 3 out here maybe. You still have 3 cubed over 2 cubed. If we invert the fraction, turn it upside down, flip it, whatever you want to call that, we can then say that 3 halves to the third is the same as 2/3 to the negative 3. And the reason, of course, we do that is because we like to match the bases here. We like to match the 2/3 on both sides. Once we've done that, then we'll just match the exponents as we did back in number 7. We'll say x plus 1 here is equal to negative 3, and insert subtract negative 1 on both sides. X should be negative 4. And you should be able to put that back in and check to see that, in fact, maybe right here if you would be kind of nice. A negative 4 plus 1 is negative 3, and 2/3 to the negative 3 is in fact 2/3 to the negative 3. So negative 4, a nice answer for number 3. Number 11 is kind of similar to number 3. We'd like to match the bases again, and you see that the bases are not the same. In this case, 9 and 3 are not the same, but of course 9 can very easily be made into a 3 by making that 3 squared. Once you have 3 squared, this is 3 to the 2x and 3 to the x squared minus 4x. I save a little space here by saying, look, this becomes 3 to the 2x. The 3's are the same, the base match the exponents. 2x should equal to x squared minus 4x. And then maybe subtracting 2x from both sides. 0 on the left equals to x squared minus 6x. We've talked about it almost every session here, factoring, right? I want to factor this. x squared minus 6x to x times x minus 6, not a trinomial. Don't make it a trinomial. Just factor the x out from both. And 0 and 6 should be very nice answers for number 11. Go back and put those both in. 0, of course, anything to the 0 power 1, 3 to the 0 also 1. And the 6 should work maybe back here. This is 3 to the 12. Put a 6 here, 36 minus 24, also 12. So it looks like 3 to the 12 equals 3 to the 12. The 0 and 6 should work in both cases there. Number 18 is not the same at all. Number 18 is a bit different. We're not trying to match bases here. We're trying to solve the equation, and we don't have more than one x as we did back in the other problems. We only have one x we like to solve for. And we'll deal with this just as we would any other equation. Maybe subtract 12 from both sides, and be left with 5e to the x equals 15. And then after that, maybe divide by 5. Okay, so we're left with e to the x equals 3. Anytime I see e to the x, I'll go ahead and for the natural log, because I didn't write it, but you should know, I'll put it back in the corner over here again, that first of all, log of 10 you should know is, and log, in fact, natural log v you should know is. In fact, in both cases is 1, okay? And log base 10, this is understood to be base 10. 10 to the 1 is 10, and this is log base e, and that'd be e to the 1 is also e. Those are two very useful items for us. Very useful here, because we have now 5e to the x equals 15. We divide by 5, and we'll take the natural log of both sides. Whenever I see e, I'll take the natural log, because I'd like to then proceed to have the x come forward and realize this natural log of e is nothing more than 1. So we're left with x here equal, on the left equals to natural log of 3. Again, refer you to your natural log table here. Again, caution you, be careful. Make sure you're using the proper table. Natural log table, natural log of 3, about right here, and I'm looking at 1.099, which is a good answer for us. We can underline that one and say, look, we finished number 18, just as we would any other equation. Difference being that we like to get the x out of the exponent here by either taking the common log or the natural log of both sides. That's 18. And 23 is kind of similar. We'll go ahead and try to do the same thing. Try to get the x by itself by first subtracting 8 from both sides. Subtract 8 from the 35, you'd be left with the 27 there. And lastly, maybe dividing by 3 on both sides. And you get 2 to the x is 9. Again, not 2x equal to 9, but 2 to the x is 9. And this is what we like to do, either take the natural log or the common log. Either way, I took the common log this time for a change. I usually revert to the natural logs. Go to common log just to show you it doesn't make any difference whether you're taking a natural log or a common log. The natural log, very, very useful with the e. And back here with the 2 to the x, you could have taken the natural log or the common log, get the same answer. I've taken the log of both sides and saved a little bit of time getting close to the bottom here. So I take the log on the left, the x will come forward. You'll be left with x log of 2. On the right side, log of 9. And then, of course, to get the x by itself, divide both sides by log of 2. Check the table again, this time the common log table. The common log table for 9 or 9.00. And just to verify that, I'm looking at 0.9542. 0.9542. The common log of 2 is 0.3010. Again, I would not expect you to divide by 0.3010. I'd expect you to round this probably to 0.3 and then just move the decimal one place above and below. You can see that 3 goes into 9 3 times already. And divide it a bit further. 3.18 should be a nice answer for us, okay? So with these 5 problems, we've done quite a few different things. We've dealt with the matching the exponents, and then we've also proceeded to say, how about dealing with equations where we have to change a bit, and then here the equations where we have only one x, but to solve for that x. And I think I'll probably need a little cleaner here and to clean off the board and proceed with a bit further. Looking at number 26 next. 26 is 4 times 10 to the 3x equals 20. Be careful, this is not 40. You don't multiply the 4 times 10. Remember, what we do is we proceed to deal with the exponents first and then multiplication and division. So you don't want to call that 40. In fact, what we like to do, just the reverse of this, we like to get rid of the 4 by maybe dividing both sides by 4. Okay? How about saying when we divide by 4, 10 to the 3x equals to 5. Okay, 10 to the 3x is 5. With that situation, then when I'm looking at that 10, I'd like to take the common log of both sides. I'll do this once and maybe try to skip this step a little bit later. Log 10 to the 3x equals 2 log of 5. You should recognize the fact that the 3x will come forward, and log of 10, I just erased back here a minute ago, should be 1. So this is just 3x over here is equal to log of 5. And what we'll do is to proceed to find the log of 5 from our log tables. I find the log of 5 as 0.6990. Do that please if you would, and make sure that you get the same answer there for log of 5, not the common log of 5, but the natural log of 5, 0.6990. Divide both sides by 3, and I think we have it. Divide by 3 on the left and 3 on the right. How about x equals to 0.233, okay? A nice straightforward problem, kind of standard. It's 26, you'd think it might be maybe closer to the first few, but it's not that bad. 26 finished. Let's push on to 32. Is e to the 2x minus 4e to the x minus 5 equals 0. And this one looks kind of difficult because first of all there are 2 x's instead of 1. And then secondly, can we factor this? I'm going to try to factor it directly. There is something called the change of variable, which I'll show you in a moment also. But I would suggest to you, if you understand that e to the 2x is the same as e to the x squared, isn't it? Again, that's when you square this, you don't get e to the x squared here, not right. When you square that e to the x, remember when you square, you keep the base and multiply the exponents. So e to the x squared is really e to the 2x multiplied 2 times x. So we could call this e to the x squared and say if it's e to the x squared, how about e to the x times e to the x? That should give us e to the 2x. Again, multiply these two, and we'll say again, this is e to the x quantity squared. The same thing here, e to the x quantity squared, which is going to be e to the 2x, not e to the x squared. And then how do you get 5? 5 and 1. How about a negative 5 and a positive 1? I think that'll give us a negative 4. And check to see the outside is 5 e to the x, and the inside positive 1 e to the x. That should be a negative 40 of the x, and the last two a negative 5. Looks like that should be okay for us. So I try that. There's also a change of variable. I'm not sure I want to do that at this point, but I can show you that, I guess. I don't see any others that I'm going to be doing that'll work that way. First, let's finish this. If you set the first one equal to 0, this is e to the x equals to negative 1, and the second one, e to the x equals 5. And what we'll do here is we're going to go ahead and just eliminate that first one. There is no power, no matter what this base is. No power here, for whatever base I'm getting a negative 1 with. For example, e is 2.71828, but e to the 2.7 to the negative 1 is not a negative number. It's a fraction. There's no way I can get a negative number here with any exponent. So this is going to be eliminated here. We just cross that one and throw that one away. That's never going to work. E to the x is 5. You should take the natural log of both sides. Natural log of the left side will give you x just by itself. And the natural log of 5 we'll find in just a moment. We found that before, I think. Not the first time for us for natural log of 5. Natural log of 5 from the natural log table, looking at maybe 1.609. 1.609 should be a nice answer. I'm going to try to do the same problem here in this board. I'll erase it a bit if I could. I hope it'll dry quickly. Because there's another way of doing this. I'm hoping you can see the factoring, and some people can't. Again, you'll have to go through the same routine I did back here, but what we could do is, we could say, let's change the variable just for a minute, and then solve it in that variable, and then come back and go back to the original variable. It's as if you were translating or speaking in a foreign language. You might want to go ahead and speak in that language and then translate it back into the language you're familiar with. We do the same thing here. We can go ahead and say, look, let's change that e to the x. Usually the middle one here is useful to us. Now let's change the e to the x to maybe a y, okay? See what that will do for us. Let here e to the x equal to y. Let this one right here equal to y. Again, realize that as we said above here, that means that if we square both sides here, this is not e to the x squared, it's e to the 2x. E to the 2x should equal to y squared. So here's e to the 2x. I'm going to call that y squared. I'm hoping that maybe the green will pick up here. E to the 2x, I'm going to call y squared. E to the x we identified right here is y minus 4y minus 5 equals 0. That might be easier for you to factor. I think you probably factor it directly, it's not that bad, but if you had to do this, that'd be good too. And then of course, proceed to factor this as y minus 5 and y plus 1. And then you get y equals to 5 and negative 1. And the important feature here is do not circle the 5 and negative 1. Y is nowhere in your problem. You inserted y. So go back now and change y to what we said y was, e to the x. So call e to the x equal 5 and e to the x equal to negative 1. As we saw, we throw this away. Natural log of both sides, x equals natural log of 5. And we'll get the same thing I had a moment ago. I think that was 1.609. 609. So there's an alternate way of doing this one if you're interested. It's called change of variable or change of changing the e to the x to some other easier variable y and then proceeding with that. And the important feature is do not stop here. Do not stop at y equals to 5 and negative 1. You want to proceed to say, wait a minute, let's change back now to what y was, e to the x, and then solve it there. So your choice on that one. I kind of like the factoring it directly, but if you're not interested in that, then you can always use the change of variable. Now that's 32 for us. We're going to push on from there to 34. 34 is a lot nicer, a lot easier. The author already did the work for you, okay? 34 is 3 to the x minus 3 to the negative x in parens, and then 3 to the x plus 3 to the negative x, also in parentheses, equal to 0. It's already factored for you. Let the first one equal to 0. And of course, let the second equal to 0. The first one, add 3 to the negative 3x on both sides. You'll get 3 to the x equals 3 to the negative x. And over here, 3 to the x equals 2, subtracting negative 3 to the negative x. Now just as a moment ago back here, we said, look, you can't have this. You can't have a positive. There's no variable here. Nothing I can get here for x. It's going to be a negative number. So I'm going to have to throw this one away. That's not going to work at all. This one will work, believe it or not. The base are the same. The exponent should be the same. And the only way, of course, those would be the same is if x is 0, right? Okay, so x is 0 should work very nicely for you. But check it back here if you would. 3 to the 0 is 1, minus 3 to the negative 0 minus 3 to the 0 again is also 1. 1 minus 1 is 0. This one, of course, 0 times anything, who cares, will be 0. Looks like 0 should be a good answer for us for 34. So actually, 34 is a lot easier than 32 back there. It's kind of already done for you because of the factoring already done. You only got 3 problems there, and I still need a handful more. So I need to go back and erase this. So this might be a good time for a coffee break while I'm erasing the board. We're moving on to 36. 36 is a fractional equation. 17 over e to the x plus 4 is equal to 2. Now normally what I would do would be say, call this 2 over 1, and this is a proportion. We have one fraction on either side of the equal sign. You could just interchange the means if you want to here, or you could multiply both sides by e to the x plus 4 on either side there. You could do that if you want. I'll probably do that, but it's so much easier just to interchange these. We'll get in a moment if you interchange these. E to the x plus 4 equals 17 halves. If you multiply both sides by e to the x plus 4, e to the x plus 4 on the left will just give you 17, and this will be 2 times e to the x plus 4. And then since we want to get the e to the x plus 4 by itself, we want to divide by 2, 17 over 2, okay? So basically, had I just reversed these two, they're called the means there, get the same situation without going through that extra step. But your choice, either way. At 17 halves, I would change that probably to a decimal because we're dealing with a decimal table. So how about the 8.5 on that one? And that's equal to e to the x plus 4. And then probably want to subtract that 4 very quickly here. How about e to the x equals to 4.5? Okay. And you should know what the next situation is here. You see that e, so you want to probably proceed to say, let's take the natural log of both sides, okay? So I take the natural log of both sides, ln here on the left, and ln on the right. The natural log of e is going to be 1, that's going to be x out here, x times 1. And natural log of 4.5. Natural log of 4.5 from your natural log table, go down here to 4, and then 4.50. Basically, I'm looking at 1.504. So 1.504 should be a nice answer for us. Kind of quick statement, not too bad. A fraction, didn't turn out to be too bad. 36. After that, we need the 38, which is kind of similar. Give you two examples of each type here. 38 is 4 over 3 minus e to the 3x this time is equal to 8. And again, I think interchanging these would be very nice. In fact, let me just do that because I'd like to introduce you to something that's newer here, if we could. If you multiply both sides by 3 minus e to the 3x, you'll get a 4 here and an 8 there. And then divide by 8. Basically, what's going to happen is this. You can interchange the 8 and the 3 minus e to the 3x and be left with that. Give it a try, okay? Do as you probably would. Cross multiply, I would guess, might be another way of doing it. And then divide by 8. I think you'll find that gives you the same answer, okay? So this will give you 1/2, maybe 0.5 back here. And that's equal to 3 minus e to the negative 3x. Let's subtract 3 from both sides. The minus sign back here with the e. This is plus sign, so subtract 3. I think when you subtract 3, it should be 2.5. Check me on that, okay? In fact, subtracting 3 will not give you 2.5, it will be negative 2.5, right? Subtract 3, let's put the negative 3 in there to be certain. Be careful with the signs, okay? Yeah, I think negative 2.5 would be nice. I'm thinking that because there's a minus sign in front of this negative e, and there's no way we get an a, taking the opposite here, have a negative on the left. When we take the opposite, we need a positive there, otherwise we have no solution, as we saw in a few other problems. So looking at something like this, e to the negative 3x is equal to 2.5. After that, let's proceed then to go ahead and say, okay, how about taking the natural log of both sides? And natural log on the left is natural log of 2.5. I should just put maybe right there in purple. Natural log of 2.5, natural log on this side, and negative 3x, okay? Natural log of 2.5. Natural log of 2.5, looking at, oh, in fact, my mistake here, the negative was never there. Yeah, I don't know how positive became a negative, that's not right at all, is it? But let's get rid of the negative there. Yeah, that won't affect anything we've done so far, we haven't come that far yet. But this should be a 3x throughout there, there we go. It wouldn't have made a difference with the negative either, but in this case, the problem had a positive 3, and it should remain a positive 3. Natural log of 2.5. Again, looking at our natural log table here, natural log of 2.5, looking at 2.5 is 0.916 on that one. So I'm going to say 0.916 equals to 3x. And dividing by 3, kind of easy there. 3 and a 9, 3 times. 3 into 0, or 3 and 1, 0 times. 316 about 5 times. How about 0.305? Okay? Good answer for us then for number 38. Be careful with the signs there. Aside from that, it's a rather straightforward problem. There are quite a few steps there. Just take your time. After 38, we'll look at 42. And 42 is log base 2 of 3x minus 1 equals to 3. And notice the difference in each of the other cases. We were talking about exponential equations. Now we're looking at a logarithmic equation, aren't we? So we've changed back there using logs. Here we're probably going to change the other way, and because it's a log equation, go back maybe and talk about the exponent form. You should know how to do this. We've done this in the previous sessions. You're going to say base 2 is not helpful to us at all, but we can go back and say, look, this base 2 raised to this exponent 3. Remember back here, a log is an exponent, right? How about 2 to the third, this base raised to that exponent equals to this number, 3x minus 1. Well, that's too easy for us, right? Yeah, that's kind of nice. These are easy equations, easy problems. Go back and change to the exponential form, and this base 2 to the third power, 2 to the third 8 is equal to 3x minus 1. Maybe add 1 to both sides and divide by 3. How about x is 3 in fact? And check this real quick. If you put a 3 in here, this is 9 minus 1. That becomes 8. Is that true? Is this base 2 raised to that exponent 3? Is 2 to the third equal to 8? Again, 2 to the third, not 6. 2 to the third, 2 times 3 times 2, in fact, is 8. Good answer, okay? Doesn't take long to check that one. There's 42. After 42, we'll push on to 46. Now 46 is kind of similar. There are at least 2 examples of each. This is log of x squared plus log x equals to 3. In this case, we don't have just one log, we have 2, but we'll have recourse now to our rules. Let's go back and try to get one log instead of the 2. Get something to look like number 42 if possible. What about that plus sign? When you're adding with the logs, it means you're doing what? You're multiplying with the numbers, right? So we go back and change this addition to log of x times x, x squared times x. How about log of x cubed? How about log of x cubed equal to 3? That sound better for us? And then from here, I'd probably say, look, log of x cubed. How about going through the definition? This is log form. Let's go back to the exponent form. I was just going to say x cubed equals 10 cubed, but let me go ahead and put this in anyhow. You should understand that there's no base there. It should be base 10. So back through the exponential form, this base 10 raised to this exponent, remember our log's an exponent, raised to that exponent 3 should equal to this number x cubed. Now most of the time we're trying to get the bases the same, and once those are the same, we say the exponents are the same. It works the other way too. If the exponents are the same, the bases must be the same, right? So nice and easy, real quick one here. How about x is 10, okay? X is 10. And that should work very nicely for us. If you look at this as 1,000, what's the log of 1,000? 10 cubed. The log of 1,000. 10 to what power is 1,000? 10 to the third power. That looks pretty good, okay? X is 10. A nice answer for us for number 46. I think we have just about 3 more to do, and 1 more board should do it. Let's see what we can do with erasing this and put the last 3 up for this session. And this session is really a nice one because it combines much of the chapter on logs. The only thing we haven't done so far is to deal with the applications here. And these are nice to deal with the logs and all forms of equations, but the applications are really great. And the next session is where we'll deal with that, okay? I have on your Canvas files there the applications worksheet, so I ask you to print that off, please, so that when you look at the next session, you'll have that available. I'll be reading it also, but it's nice to see the answers there, the problems there first. And then I have the answers, I think, on the last page of that. So print off the answers for yourself, too. We'll probably get the same answers, hopefully, as what's in the back.
Sometimes we'll miss by a decimal or two, but again, that's not terribly worrisome to us. What we're concerned with is getting a nice answer. These are approximations anyhow, so if we miss by a decimal here or there, that is to say, 3.1 or 3.2, not 3 and 30. That's missing a decimal, but it's the wrong place. Missing one decimal place at the end isn't too bad for us. All right, we're on to number 48. Number 48 is kind of similar to the previous one, 46. By the way, I think I'm probably asking you to do the odd ones here, so give those a good try. Do check the back of the book on them, okay? This time it's kind of similar, but we're not using the base 10 anymore. We're using base 2. That doesn't make any difference, as long as they're both base 2. If they weren't both base 2, we have a big problem on this, okay? Because the rule said that when you're multiplying with the same base, not with different bases, multiplying with different bases, you couldn't combine them at all. This is 48, log base 2 of x minus 1 plus log base 2 of x minus 3 equals to 3. Let's do the same thing we did in the previous problems. Let's proceed to get these together as one log, and you should understand that the plus sign here means we're multiplying. So how about log base 2 of x minus 1 times x minus 3 equals to 3, okay? Looking at that, and then after that, we'll say, okay, that's nice, we put those together. Can we do the same thing we did in the previous problem? Can we change back to the other form? And you should know the other form. This form is, I'll wait, no response. LOG out front, this is log form, right? The other form should be the exponential form. It's going to say this base 2 raised to this exponent 3 is equal to this number. In fact, this number x minus 1 times x minus 3. We have a quadratic in a moment here. And this is 8 on the left. And how about x squared minus 4x plus 3? And check to see if that's okay for us when we go ahead and FOIL that. The outside 2, negative 3x, and negative 1x, negative 4x, and the last positive 3. As with any quadratic, we'll try to get this equal to 0 by maybe subtracting 8 from both sides. Subtract 8 here, maybe I'll put that in so you can see it. Subtract 8, subtract 8, we're looking at negative 5. And that should be factorable. Again, factoring is extremely important. Practice it if you need to. How about x plus 5, x minus 5, and x plus 1? Again, outside and the inside, make sure those are right with the signs. I think we'll get a negative 4 and a negative 4x and a negative 5 out of that. When you set these equal to 0, the first one will give you x equal to 5, and the second one x equal to negative 1. Negative 1 might work. We'll find that later that there's no problem with the negative 1, provided it doesn't give us a negative number here. Because 2 to no power will give us a negative number. We saw that before. So I don't think negative 1 will work here. Had it been maybe plus 4, negative 1 plus 4 would be positive 3. That'd be great. That'd be great. But in this case, it won't give us a positive number. We're going to throw that away. Okay, so be careful. Go back and check. Putting a 5 in here should work though. This is maybe 5 minus 1. This is 4. And this is 5 minus 1. This is 2. Let's check to see if that's true. 2 to what power is 4? 2 to the second power. This whole thing, log base 2 of 4. Log base 2 of 4 should be 2. And here, 2 to what power is 2? 2 to the first power, or log base 2 of 2 should be 1. And is that in fact 3? Absolutely. Looks like a good answer, okay? So 5 is a nice answer for us for number 48. Do discard the answer if it doesn't work. Go back and check. Okay, you'll have time to check these, so do a good job on the checking, okay? There's 48. We have 2 others to do, the 60 and 62. And these are kind of the ultimate, we're finished with them. The natural log of 4x minus 7 equals 3. ln of 4x minus 7 equals 3. And actually, I probably wouldn't even have written that, but I wanted to show you that we write down the problem, and then I would probably instead say the natural log is log base e, okay? Because we're going to change that. We're going to go back later and proceed to go back to the exponential form. The exponential form would say this base e raised to this exponent 3 should give us this number, 4x minus 7. Okay, there we go. All we need to do now is find e to the third. And again, if you've been following the other sessions, you know that there's some things you should have printed off already. And what you should have printed off was an e table, okay? And we haven't had a chance to use that one yet, but we're going to use it right now. The e table is this table, and it's a situation where we have the x forward, and we'll look from 0 down here to 2, and then from 2 to 4, and then from 4 to 6, and then we have e to the x and e to the negative x. So we have two considerations there. In this case, we're looking for e to the third, so we'll go down to 3, which is about here where my finger is, e to the third, about right there. And that looks like 20.09. The next number in the next column over is 0.05. That'd be e to the negative 3. We're looking for e to the 3. How about 20.09? Okay. So looking at 20.09 here, 20.09 is equal to 4x minus 7. Add 7 to both sides. 4x is 27.09. And then divide by 4. Okay? So, rather easy problem. It's natural log this time. We changed the natural log to log base e. We proceeded to change back to the exponential form, e to the third equals to 4x minus 7. After we found e to the 7 from our table, we proceeded to add 7 to both sides. Divide by 4. I'm going to go ahead and say that when you divide by 4 out of 27.09, you should get 6.77 is what I have, okay? 6.77. And check me on that. That shouldn't be very tough to check. I think we have a good answer there. It looks like 4 goes in at 27 6 times anyhow. 7's a bit too big, be 28. So 6.77 looks like a nice answer. Okay, that's 60. Let's get the last one here. And we'll say we've done all that we needed to do with the logs. And what we need to do after this is to go ahead and apply this. And that is, say, will be the next session. Looking at 62, it's the log of x squared plus 4 equals to 2. I try to choose one with natural log and one with log. In this case, it's the log situation. You know that log is base 10. So to go back to this and say base 10 raised to the second power should equal to x squared plus 4. This is 100, should equal to x squared plus 4. And subtracting 4, that's 96. And the square root of 96 is what we're looking for. And the square root of 96, we would normally probably factor out the perfect square, which probably is about a 4 in there, and get it in simplified radical form. But you see in each case here, we're talking about the numbers with the decimal. So I'd ask you in this case to go ahead and get the decimal form, okay? Instead of the simplified radical form. And I think the author will do the same too, okay? This is 62, you won't see it, but maybe 61 on yours. If you're doing that, you will be seeing it that way. Let's take a look at how we can get this without a calculator, believe it or not, okay? We'll get a very nice answer for this without a calculator. Radical 96, I'm thinking, is this. I'm thinking radical 96 is between radical 81 and radical 100. Hope you'll agree with that. Radical 81 is 9. Radical 96 should fit in here somewhere, and radical 100 is 10. So it looks like radical 96 is 9 point something or other. We'd like to find out what exactly is it 9 point and get a little bit more accurate on that, okay? So there's a very easy way of doing this. If we're looking at numbers between 9 and 10, then I would probably try 9.5 and check to see, you know, what the definition for radical is. Is that number 9.5 times 9.5? Will that give me something close to 96? I'm going to try it over here. I have over the space. Go back here and try it over here. Looking at 95 times 95. 95 times 95. I know you're groaning, but isn't that bad? 5 times 5 is 25 and a 2, 47 maybe. 9 times 5 is 45 and a 4, 81 and 85 maybe. That's 5 and 2 and 9, 0. Looks like 90.25. Well, we're looking for 96. We tried 9.5 halfway. That didn't quite make it. We need to have something bigger. So I'm going to say, okay, between 9.5 and 10, because we're going down, it has to be between 9.5 and 10. We tried between 9 and 10, 9.5. So now we're looking at between 9.5 and 10, between these two numbers. And I'd go halfway. Halfway, you know, think of it as 950 and 10 or 100, and maybe 975, 9.75, okay? 9.75, that's halfway between. but instead of 9.75, I'd probably ask you just to do 9.8, okay? Don't ask you to multiply those numbers. 9.8 should be nice, I think. Let's give it 9.8 a try. See if that works, okay? We're trying to check to see how close that comes to 96 for us. 9.75, let's try 9.8 times 9.8, okay? 9.8 times 9.8. 8 times 8 is 64, and is 6. 72 and 6 is 78, sounds like that. 72, 9 times 8, and a 7 here. That looks like 81 and 88 there. How about 4 and 0 and 15, 6? Oh, look at that. I got too close on that one. Didn't expect that one to come out that nicely, but it does. Okay, it looks like we're looking for 96. We had 96.04. Very, very nice. So let's say that then the radical of 96 is right here, 9.8. Looks pretty good. Go back and be careful, though. We kind of were concerned here with finding the numerical value of it. We're looking for x, and we should have probably put the plus or minus in there, because I think plus or minus will work. You know, back here in number 48, we threw the negative away, it didn't work. But I think in this case, the plus or minus should work for us for 98 here. If you put it here, if you 9.8 times 9.8, approximately 96, and we saw that. Positive or negative. A negative 9.8 times a negative 9.8 will be a positive, as we said, a positive 96. So either way it's going to work. 96 plus 4 is 100. And this base 10 raised to the exponent 2 is in fact 100. Looks good, okay? So go back and check to see. In most cases we'd say the negative will not work. In this case we had x squared. When we square that it will be positive. Good answer. Okay? Now, this kind of completes our discussion of logarithms. At least the algebraic part of it. We're going to look at the nice applications of this, because again, they're nice to play with, the logs, kind of fun, and involves quite a few things, the factoring and also the bases and exponents and all those. But the applications are really important too. The logs are used quite a bit in applications, and we'll see that in the next session, session 21. I ask you, if you would, to again proceed to print off that session 21, the log applications worksheet, and then we'll be working on that, and that will finish our chapter for logs, and we'll then be ready for a test on this. But we'll worry about the test a little bit later. For right now, we want to finish off the application. So this one, session 22 on page 320, session 20 on page 322. Again, take care of printing off the applications worksheet, and we'll see you for next time.